let's continue to discuss this equation with a slightly different point of view. Recall that we've already drawn a slope field of this, and everything in that slope field essentially depended on the function sitting on the right-hand side in this differential equation. Now, let's actually plot this function. So, in this graph, we're going to have the horizontal axis represent the y-axis, and we'll draw a sketch of the function f of y. For y close to 0, f of y will be well approximated by the lower power, so it'll be approximately equal to y. Far away from y equals 0, f of y will be approximated by the larger of the powers, so it'll be behaving approximately like minus y cubed. Let's assemble that on this diagram. So close to the origin, the function will be well described by a straight line of slope 1. Further away, it's going to be a minus cubic curve, and therefore we can imagine that the function is going to look sort of like this. And in fact, we can be more accurate by identifying the places it crosses the y-axis. These are the zeros of this function, and they are at y equals minus 1, y equals 0, and y equal 1. So these 3 points are what we call steady states, and they are characterized by the fact that there's no change at that point. dy by dt is 0. Now, let's observe what happens when we're somewhere between the steady states. Suppose we start initially at a point somewhere here. Well, the corresponding value of f of y is above the axis, it's positive, and that gives us information about the rate of change of y. And let's recall that increasing y is going to be in this direction. This is y increases by convention. Decreasing y is in the opposite direction. And so if f is positive and y is increasing, we're moving towards this steady state. And that happens all along this particular interval for y between 0 and 1. Now what about over here? Well, over here the function is negative, and so y has to decrease. We're moving again towards this steady state from above. We can do a similar analysis in this part of the diagram. Suppose we were to start off with an initial condition somewhere here, then again we see the function f is negative, which tells us y is decreasing. It's moving to smaller, more negative values, and so we're moving in this direction. And similarly, over here, we can deduce that we're moving the other way. So altogether, we found the steady states, and we found the directions of motion, and now we can say something about stability. Notice that when we get close to this steady state, all the arrows point inwards, which means if we start nearby, we get closer and closer. And therefore, this steady state will be called stable. The same is true of the steady state at minus 1. The arrows point towards it. Again, this makes it a stable steady state. On the other hand, let's see what happens close to 0. If we look close to 0, then initial conditions near here diverge. They get farther and farther away from 0. And when that happens, we say that this steady state is unstable. So altogether, we found that there are 2 stable steady states at y equals 1 and minus 1, and 1 unstable steady state at y equals 0.